All right. Hi, everyone. I'm Smeet, and I have been working with PyTorch and optimizing it on the A64FX processor. So most of you might know what is machine learning, but just if you don't know that, it is applied to many production systems today that you are very likely using, such as your smartphones, which have an assistant, a smart assistant like Google Assistant or Siri, or your traffic cameras where they can capture number plates. So it does basic optical character recognition. So that is machine learning. Now, to be able to do that, there are different libraries and frameworks. So I have been working with PyTorch because it is relatively straightforward to build and easier to work with. It has so PyTorch is an open source machine learning library based on the Torch library. So it has a C++ backend and a Python front end. PyTorch provides tensor computations with strong GPU acceleration and reverse mode automatic differentiation, which basically means that it computes the forward pass, and then after calculating the outputs, then it calculates the backward pass. For our experiments, I have worked with version 1.10, which is the latest one available, and it has support for 1DNN, which I will talk about it later. So these are some of the different compilers and BLAST libraries I have used. So Fujitsu in Clang mode with their scientific subroutine library, SSL2, the ARM compilers with their ARM performance libraries, and the GNU compilers with the ARM linking it against the ARM performance libraries, OpenBLAS version 0.3.19, and Bliss. So these are some of the compiler flags that I've used. So these are the fixed flags. Each individual software had its own set of flags that it was using. So while it says O fast or K fast, it may not actually use that. So the build process. So we built Python from source with O3 optimization. Just before installing Python, we recompile the object file and link it against the specific BLAST libraries. So this enables any other libraries such as NumPy, which have a C backend. They can make use of these a lot of the BLAST library functions. So now we move on to PyTorch. So PyTorch is built with 1DNN. So if and people don't know, it is part of the One API toolkit that Intel provides. It was formerly known as MKLDNN. So I might switch between 1DNN and MKLDNN when I refer to it. So Fujitsu was able to achieve this by creating a JIT assembler, and they use this software called Kaibiak Art64. It's pronounced with a K, and they develop it for the ARM processors, and that helps them enable assembly coding to port 1DNN. And now this work has been upstreamed to 1DNN, which makes it very relatively simple to use with the new versions of 1DNN. That's why 2.4.3 is one of the latest ones that can PyTorch can build. There is 2.5 which is released, but it does not have the entire compatibilities, so I have not used that. And to make PyTorch build with these different compilers, the small software patches have been applied across. So, and the largest one is to the CMake files to find the BLAST library so that it can recognize SSL2, the ARM performance libraries, OpenBLAS and Bliss. And finally, for distributed training, we use Horovod, and that is built with OpenMPI. So for Fujitsu compiler, we use the one that they have provided, which is based on 4.0.1, but they have compiled, they have modified it a lot. And for the ARM and GNU compilers, we use 4.1.1. So this is one benchmark application from a well-known problem called domain generalization. And the data set that we use here is the PAX data set. You might see that there are very few images here, but the reason to use this data set is to see how well different batch sizes can fit on a single node, and these transforms that you see over here represent the complexity of the problem. Okay, so model training and inference can be improved using different memory formats. So NCHW stands for the number of images in a batch. C for channels, usually if it's a RGB, so that can be 3, or grayscale, which would be 1. H and W stand for height and width of the image. This is the default memory format for images in PyTorch, and NHWC is just switching the, NHWC just reorganizes the entire tensor, and that is the default in TensorFlow. And the new ones where we have NCHW16C, which is also known as the MKLDNN format, is the block format, which helps us use SVE basically. So we use OpenMP number of threads of 48, and the Fujitsu provided the environment variable, which is the XOS MMML HPH type equals none, which basically disables the use of huge pages. And we use TC malloc for memory allocation. We don't build it with TC malloc. It's just during execution, we just preload it, LD preload. So these are the numbers that we have seen. Lower is better. And yeah, so it was very surprising. I ran all the scripts multiple times, but we see that the new compilers perform quite well with irrespective of the BLAST library compared to the Fujitsu with its SSL2 and ARM and with its ARM performance libraries. Now that is with the block memory format with 1 DNN. So to test the actual the outputs or throughput for the without 1 DNN, that is why we have the second step where we just use it on the base format and we disable 1 DNN. This has to be explicitly disabled because it comes in a partial mode where convolution operations are in MKLDNN format, whereas other operations are not. So that's why it has to be explicitly disabled. And here, all the operations are defined in the A10 tensor core library. So here we can see that the Fujitsu's BLAST library does a very good job. And so the performance difference is not that different. It is relatively great. OpenBLAS is not is performing quite well for the new version, which is 0.3.19, which has it has support for A64FX. And if you will notice, I have not included Bliss here, and that is because it does not have full support for different SVE instructions or their built-in routines. And so Bliss was built locally on A64FX. It does not directly recognize the CPU, so I had to build a generic version. And while building PyTorch, it does not support layback. And that is a very fundamental thing which has helped improve the other libraries. So the epoch time, an average epoch time for this build was about 10,000 seconds. So over here, you can see the speed up where the Fujitsu libraries have about 29%, 29 times, sorry, it's not 29%. And OpenBLAS also has 10% speed up. So this has been seen only in the newer versions because SVE enabled and optimized SGEM and DGEM kernels have been added recently, I think as of December. But there's a bad performance has been seen even in the prior version, which is in 0.3.10. Now it is important because 1DNN itself does not have all operators. It does cover a lot of your common operations, which can be seen in commercial applications. But not for scientific applications, it is possible that there are some operators which are not defined. And in that case, what one has to do is that they have to fall back to the default operations. So PyTorch default operations are in NCHW representation. So it is better if we can have, if our build uses one of the better BLAST libraries. So in that case, it would be the Fujitsu compiler with the SSL2 BLAST library. And so moving on to distributed training, I use the CIFAR 10 data set, which has slightly more, about 10 times more images. So 50,000 images are kept for training and 10,000 for testing. The batch sizes have been fixed across, and we have tested two configurations. One is using one process per node, and the second is using one process per NUMA region. So that would be 4 processes per node basically. And that is very useful to know, because the data set is sharded and each shard is given to a separate process. So at 128 nodes, there would be 128 pieces of the data set in the first case, whereas in the case where I have one process per NUMA region, there will be 512 pieces of the data set. So here are some of the scaling results. At the top, you can see that is where I have used one process per node and 48 threads per process. And at the bottom, it is one process per NUMA region and 12 threads per process, so as to not cause any oversubscription issues. One interesting thing to note is that the new compilers with OpenMPI behave weirdly. As you can see over here, the distributing the job towards the second node itself does not perform better than the first one. It is approximately the same. And even after that, we see that it is still slower than the other compilers. Over here, I have not included OpenBlast because I ran out of time and there was too much to compute. So that to show the results, the images processed at 128 nodes was about 30.75% of the number of images computed for a single node. So what that means is in the single node case, there were 500 images processed by this compiler, but at 128 nodes, it dropped down to 153 images per second per node, which is how we realize the communication bottleneck eventually steps in. The number of images are not that bad over here because it performs only 59 images per second per node, and it drops down to about 38 over here. So that's, as I mentioned, there was a scaling discrepancy, and to see what happened over there, Horovod itself provides a logging function, and the trace files showed that the communication was the larger bottleneck, where the negotiation operations were taking a lot of time. And this was reproducible across different compiler versions of GNU and OpenMPI. So I'm still looking into that. And just to for fun, I wanted to see if we could use the Fujitsu's SSL2 library with the GNU and ARM compilers. So it is possible to build 1DNN and PyTorch both with their libraries, but we run into segmentation faults for some operations. Basically, convolutions failed, which is a major drawback. But with PyTorch, I was able to run linear neural networks without any errors. So it might be possible. Tony suggested that it might not be ABI compatible, which could be true. And if anyone has ever tried to look at the shared libraries provided by Fujitsu, you will see that they are statically linked. So it is hidden from the standard linker. And to sum up, single node training run showed significant improvements with using 1DNN. GNU compiler outperforms Fujitsu compiler, but the Fujitsu's BLAS library has a major advantage over the other compiler of other BLAS libraries. Distributed training runs have a better throughput when using one process per node because fuse operations lead to low kernel launches. However, the communication bottleneck still needs to be addressed because the throughput reduces as you go higher. The Fujitsu compiler outperforms ARM and the GNU compilers with respect to scaling. And I would like to thank Tony, Eva, and the entire Ookami team for their help and sharing knowledge, and the Slack channel and the office apps, which are always fun. So please stop by. Thank you.
Thank you, Smeet. Awesome, thanks, Smeet.
So there's a question from Matthias in the chat.
Oh.
Yeah, he asks if you can share the instructions how you compiled libtorch.
Okay, sure. So there is a GitHub link where Fujitsu have provided instructions, and I have based most of whatever I have done on that, but I can send you the instructions. Yeah.
So Smeet, let me jump into the this translator, XBIAC translator, I don't even know how to pronounce it. So it seems to be a more universal tool than I initially understood. So it basically just takes object code from x86 and translates it to R.
Some of them, I don't know if it does it for all instructions, because they took help of engineers from Intel and the person who created the original XBIAC assembler.
Okay. I think John Linford's still on the call. John, do you know about this tool, and can you comment on its limitations?
I was just wondering if that's the standard JIT compiler that I've heard is used in PyTorch. So maybe these are this might be like a half measure to moving that JIT compiler towards a native ARM implementation, but I don't know. I'd have to. I'm sure. Actually, I know the guy here who would know, but I can't seem to reach him.
Okay, cool. And then Smeet, I had another question on your slide number 6. Are these basically the same calculation but using different memory layouts, or are they just two different things?
Yeah, so these are different memory layouts, but the problem size is same over here, and I mean it's same over here and same over here. Okay. So this shows the runtime, and also I forgot to mention, but the memory usage is lower over here. Yeah.
Okay.
Okay, I think there are no more questions. Thanks a lot, Smeet, for the presentation. Well, maybe we have a few more minutes for some general discussion for people who still have a few minutes time.
Sorry, it's me, Gaurav. So I have a question, like very generic question. So like, has anyone tried 1DNN with ACL, ARM Compute Library?
I have, yeah.
So
for the code I was running, it wasn't using any of the optimized kernels, so I couldn't.
Because I know something about that, like so 1DNN and ACL, I mean 1DNN plus ACL, they're having certain issues because of the memory block. So it uses channel last and PyTorch uses channel first. So that was something, and so I wanted to know, like, how's the result with TensorFlow and PyTorch, 1DNN plus ACL, if someone has done. So that is one thing. And second thing is, like, I think, John said this thing. So yes, this XBIAC thing, I don't know how to pronounce it. So it is the JIT kernel actually added to 1DNN. And there were a few performance bottlenecks because of this initially, but I think they're merging upstreaming for the new ISA 8.6, I guess. Yeah. Sure. Thank you. And sorry, just to continue on that, one more thing. So I saw so many experiments and all. It's really overwhelming and really nice to see, like, so many experiments being performed on Ookami. So do we have any GitHub repository with the course or results version, like version 0.1 or something like that, with all the applications, so that it can add to reproducibility, basically? So like ML Commons, do we maintain something like that?
This is now a question for everyone. Is that right?
Yes, sorry. Yes, Robert.
We have some bits of this for just the software coming out of the project itself, but what you're seeing here is really the community working, and each piece of these codes are managed separately. But you're putting your finger on a really important thing here, is that, well, the two aspects of sharing as a community, and then also scientific reproducibility. John and his team maintain build instructions, and I think maybe even some benchmark data on the ARM Wikilab site, is that right?
That's right. I'll post a link here. This is the one. There we go.
Right. So there's a bunch of stuff there that's really, really useful, but it doesn't go as far as what you're looking for, which is kind of like a curated data set about everything that's happened on Ookami. And well, I would say maybe the proceedings of this workshop, if we can collect everyone's slides together, would be an initial step towards that. But there are so many different codes with so many different licenses that collecting them all together in one place is just really not possible. So what we really want to do is collect the shared experience.
Sure, thank you.
So we did unfortunately run out of time, but the upside of it, we had lots of good discussion, as Ava said, and so I think in the spirit of actually finishing this on time, I really like to thank everyone for participating, not just today, but actually throughout the Ookami project. And I'd like to especially thank John and Tony for contributing the tutorials, and we appreciate everyone. And of course, none of this will be possible without Ava, and then also the HPC admin team that are standing behind it. Yeah. So any closing remarks from anyone else, or otherwise we'll say goodbye and wish everyone well.
Maybe one comment in case any questions come up, either from, I mean, the users know how to reach us, but some people who are new to the system and maybe want to use it, just reach out to us. You have our email addresses, just contact us and shoot us the questions.
Okay, very good. Take care, everyone. Bye. Be safe, keep warm.
Bye, everyone.
Bye, everybody. Thanks. Good job, Ava.